I do not. Yeah, I don't see. Yeah. Mhm. No, I mean, it wasn't doing that. Yeah, but honestly, it was, I think I did fine. I got 0-0 and I got 3-3. Okay. And for I have to figure out the even having for good. That's really true. And I don't think like executive, it's been like that. It's for what I'm. 12%. All of that. That's perfect. Yeah. Because I did. They did everything. Yeah. So do you know you did? I got yeah, I feel I think so yeah, only 30,000 others more than I give it over. I think we would have for a long time. I didn't know that. Here was I thought it was over. I'm gonna be here at 5, so I'm saying for that. So that was actually, yeah, they fairly.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing okay after the midterm? It was pretty seems like it's pretty hard. It didn't intend for it to be, but I know a lot of people took a lot of time on it. So status report on that. I'm still working on grading those. I should be done by Wednesday. I'm a little bit behind where I want to be, but you know, should be able to finish that up before Wednesday. So if you want to pick up your exam, if I see how you did, remember Wednesday is the day for that. So you can plan on being here on Wednesday. Okay. So also this is a good time to remind you of the grading policy in the class. So remember, we have two midterms exams that we're going to be taking throughout this class. One of the exams is going to count for 30% of your grade. The other exam is going to count for 20%. And so the way I determine which is 30% is just whichever one you score higher. And so if you took the exam last Wednesday and you know it didn't work out the way that you hoped, just know that you can, you know, basically kind of make up for it on the next exam. So that, you know, whichever exam that you did worse in, it's going to be worth only 20% of your grade. Okay. But if you did really well on this exam, then you can count that as, you know, like I said, money in the bank. And, you know, not that you can do poorly on the next exam, but, you know, hopefully it takes a little bit of the pressure off for the next exam. Okay. Also, you know, I want to remind you that, you know, this is an elective class, and usually for these elective classes, I like to have the overall grading average for the entire semester for everyone in the class would be around maybe like, 79, 80%. And so, if I grade when after all the grades are in, midterm, finals, everything, and I see that the overall grade is below that, what I'll do is I'll add points to everyone's grade until we reach kind of that threshold. Okay. So I don't do any curving, or I don't do any adjustments until kind of the very end. So, but just know that I am watching that, and I do adjust for that at the end. Okay. Typically for this class, we don't have a final exam in this class. It's a final project. The final projects, that's usually when kind of, grades kind of get bumped up at that point, just because, the projects are, I don't want to say it's easier, but, just the way that it's graded and kind of the amount of work that, that you guys put into it, the grades for the final projects tend to be higher than the midterms exams. At least that's how it's been for the last 3 times that I've taught this class. So, just wanted to let you know that. Okay. All right, and so for today's class, we are making a transition. So we're no longer talking about biostatics. So we're getting into biodynamics. Okay, so we're going to talk about human motion, kind of the equations that go into that, and how we can analyze that, and everything that goes along with that. So we're starting today with a I would say, fairly niche topic, a little bit of an unusual way to introduce human dynamics. But we're going to be talking about what's called the Gait biomechanics. Okay, so that's the biomechanics of walking, running, motion, and all that stuff. And so, my idea for this is to use something like Gait, which is something that hopefully is very familiar to everybody, something that you do almost every single day, that you watch people do almost every single day. And I think it provides kind of a nice stage to kind of open up and kind of introduce a lot of kind of new topics. Because everything that we went over in the first half of the class with biostatics, it's not that it's completely different, but we almost have a kind of a new whole set of terminology here. It's almost like the transition from going to from your statics course to your dynamics course. Okay, so that's kind of the transition. We're making that same transition here, except it's just we're doing it in the middle of the semester instead of from one semester to the next. Okay. All right, any questions I can answer about the exam or just the class before we get started for today? Okay, all right, so let's go ahead and get started. And so topic today is Gait biomechanics. Okay. So like I mentioned, we're making the transition to talking about human motion, and this kind of broader topic of human motion is going to basically take up the rest of our time in the semester. Okay, so starting today up until about week 15, it's all about human motion. Okay. And so compared to, biostatics, of course, human motion is a lot more interesting. There's a lot more, there's a lot more equations to it. There's a lot more, interesting scenarios that come along with it, but it's also just more complicated as well. Okay. Okay. And so in particular, we're going to spend a lot more time than usual, talking about kind of terminology and kind of standards, right? Because before you start talking about any kind of motion, right? So before we start getting into forces and things like that, we have to be able to describe the motion itself, right? And so one big part of dynamics in general is this idea of kinematics. Okay. So it's very much the same as your typical mechanics, your typical dynamics course, right? So we have to start here. So kinematics is the kind of the study, or not sort of the study, but it's the subject of describing motion, right? So what are the language, what is the terminology that we use to just simply describe, the motion in front of us? Okay. And so if you think of your traditional kind of mechanics course, your typical dynamics course, kinematics have to do with things like velocities, accelerations, the relationships between velocity, acceleration, taking the derivatives. We're talking angular motion, angular velocity, angular acceleration, things like that, okay? So some of what we describe in kinematics will be review of what you described previously in your dynamics course, but there's also a lot of new terminology that we have to do as well, okay? So we'll spend quite a bit of time on kinematics, okay? In particular, one really interesting subject that's kind of becoming kind of the gold standard now is motion tracking. Okay, so motion tracking is a relatively new technology. And I think most people are familiar with motion tracking through, maybe it's used in, making movies, making video games, making some kind of, media, right? So the idea with motion tracking is to wear, a lot of times you have to wear some kind of suit with some trackers on it, and you use a bunch of cameras to track the motion of those kind of tracking devices through, throughout the motion. Okay. So even though I think motion tracking, motion capture, there are obviously a lot of applications in entertainment, but there's also a ton of applications for science and engineering as well, right? So we're going to spend probably about a week and a half talking about just the basics of motion tracking and how that can be used to describe things like or capture things like velocities, angular accelerations, and how we can use that information for our calculations. Okay, so kinematics is a very important part when you're talking about kind of very complex motion of the human body, okay? All right, and then of course the other part is dynamics. Okay. So dynamics usually comes after kinematics. So after you have a set of terminology, a system to describe the motion, your next question is, what are the forces, or analyzing the forces or predicting the forces that cause that motion to begin with. Okay. So that's kind of similar to what we did in biostatics. And so, and for, most of biostatics, we're interested in computing things like muscle forces, reaction forces. In static situations, we can do that fairly easily with just kind of the equations of equilibrium. But of course, once you get into human motion and dynamic, it's very rare for a dynamic motion that a human goes through to be purely 2D, right? Just, naturally, just because of the geometry of our body, most motion has to be captured in 3 dimensions. So it's going to be a lot harder to do that, or at least kind of do the same kind of analysis as we did in biostatics in 3D, just because the motion is just going to be a lot more complex. Okay, so we're going to talk about different methods to do that, setting up the equations for computing forces and computing moments that cause motion. Okay. One other big thing here that I've mentioned it kind of briefly before is this idea of muscle force optimization, okay, or muscle force load balancing. Okay. And so, we've discussed before that the human body is comprised of all these different muscles. A lot of them are fairly redundant in terms of what they do for certain motions. And so how your body chooses, which muscles to actuate for certain motions is a very interesting and very complex problem. So, we'll be taking a week to kind of describe, how the body kind of goes through that and what are some methods that we can use to compute them. Okay. All right. And so one kind of prevailing theme that you'll see, throughout, for the rest of the semester is that human motion is very complex, right? A lot of times, there are kind of way too many variables and way too many equations that we can, that we can solve by hand. Even what you would describe as kind of a simple motion, like walking, right? So I think most people consider walking to be a fairly simple motion, a fairly straightforward motion, something that you do kind of without really thinking. But even very simple motions require the coordination of maybe dozens of different muscles, all kind of acting in perfect harmony. And so that's very hard to kind of do quantitative analysis of if you're just using pencil and paper. Okay. But this problem of taking a very, very complex phenomenon and trying to make it simple is not really unique to just biomechanics. In fact, you can make the argument that a lot of engineering kind of falls in this category. And so when you have this problem, you have a very complex scenario, but you need to perform some kind of calculations, you need to perform some kind of analysis. Usually there's kind of two different paths that you can take at this point. Okay. And so on the one hand, you can simplify it or you can model it. Okay. So to simplify it would be pretty much similar to what we were doing in the previous unit, right? And so we take a very kind of complex, body configuration, we simplify it to only computing just a single muscle, and then we can solve that simple model by hand. Okay. This idea of coming up with a model or coming up with an equation to kind of almost kind of like simplify a very complex situation is also very common in science and engineering. We'll be talking more about that. We'll be talking a lot about that today, actually. Okay. So this idea of kind of creating models and how to use them in certain situations. Okay. All right. And so the other kind of path that you can take when you have a very complex physical phenomenon is to use a computer to do some kind of simulation or computer modeling to kind of, do that for you. Okay. And so what I'm hoping for, so, relative to where we were kind of, last time I taught this class, we are maybe about almost a week ahead of schedule compared to where we were before. I'm really hoping that I'm going to be able to have some time to kind of talk about a certain software that you can use to model human motion. It's a really cool software called OpenSim. Okay. So I'm really hoping, I've kind of been kind of positioning myself, throughout this semester to kind of make sure we have time for OpenSim at the end, because it is a really cool software, and it's one that you can actually use in your final projects as well. Okay. But last time I taught this class, we didn't have enough time to get there, so I'm really hoping we can get there this semester. Okay. But for the majority of our lectures, just because it's just to make it kind of digestible and kind of make it easier to kind of understand the concepts, we'll be kind of focusing on this. Okay. So taking complex situations with a lot of variables, a lot of equations, and trying to kind of capture the most important aspects of it and try to use as simple of a model as possible to understand the dynamics, understand the science behind it. Okay. Okay, and kind of no phenomenon is better at that than what we're going to be talking about today, which is Gait biomechanics. Okay. So walking, running, again, usually not something you really think about, but when you kind of really start to get to the nitty gritty of, which muscle forces are acting, when they're acting, the exact motion of the knee joint, the exact motion of the ankle joint, it starts to get very, very complicated very, very quickly. And so in order for us to kind of really understand what's going on, we have to use kind of these simple models to simplify the process as much as possible. Okay. So that's the idea. So the idea, with this week's lecture is to kind of give you an overview of kind of everything, kind of the whole process of what we're going to go through when we're talking about human motion, but kind of going through it for a very kind of specific, very niche scenario of gait biomechanics. All right. Any questions on this so far? Okay. All right. So let's get into it then. So let's talk about walking first. right? Most people learn to walk before they run, after all, so it's only appropriate to start here. Okay. So walking. So walking, is I would say the primary means of locomotion for most people to move their bodies from point A to point B, right? And the way that we can describe it is basically, we can describe it in cycles. Okay. So it's basically a process of certain motions that you do with your legs that repeat over and over again. And through that process, your body moves from one point to the next. Okay. Okay. And so I'm going to draw out one cycle, or I'm going to do my best to draw out one cycle. Okay. Just so that you can kind of see every kind of important event, every important stage of this walking gait. Okay. All right. So for each of these figures, most people walk with two legs, but I'm going to highlight just kind of one leg, right? So when you're walking, you use both your legs to move, but both legs are going through the same cycle. They're just kind of offset from each other. So I'm just going to use one leg to kind of describe this whole thing. Then you can just imagine that the other leg is just doing the same thing, but a little bit offset. Okay. All right. So the first event in the walking gait cycle is known as foot contact. Okay. And so just like the name implies, foot contact is when your foot first makes contact with the ground. Okay. So you're taking a step forward, and then right when your heel, most people kind of lead with their heel touches the ground, that is foot contact. Okay. And so that looks kind of something like this. So their leg is kind of forward like this. Usually your foot is in dorsiflexion, so that your heel is the first one to touch the ground. Okay. Right, so your foot is basically right about to contact the ground there. Okay. And your other leg usually is already on the ground. Okay. Like that. Okay. The next stage in the walking gait cycle is that after your heel kind of touches the ground, as your body kind of leans forward to kind of push yourself forward, that foot then becomes flat on the ground. So the next stage is called foot flat or flat foot. Okay. And so usually it looks something like this. Person. Right. Usually when your foot is flat, your center of gravity is kind of directly on your foot. And so most of your weight is kind of on that foot at that point. Right. So remember we talked before that, when you are kind of standing on one foot, your body kind of positions itself so that your center of gravity is right on top of that. Okay. So your foot is like this, it's flat on the ground. Okay. Your other leg is kind of, kind of doing something like this usually. Okay. All right. The next stage in the walking gait cycle is that you're pushing off your foot, and so you're basically doing plantar flexion on your foot, and so your foot is preparing to leave the ground, and so the next step is what's called heel off. Okay, so it looks something like this. Usually your body's kind of leaning forward a little bit just to kind of help maintain balance, but your leg is kind of bent like this. Okay. So you're kind of pushing into the ground and kind of pushing your foot forward. Okay. Okay. Your other leg is kind of doing like that. It's about ready, to stay there as well. Okay. Right. So after your foot comes off, then then your foot kind of completely leaves the ground. So your foot needs to leave the ground for a brief period of time as you kind of step forward. So the next stage is called toe off. Okay. And so it looks very similar to the last one, but right when your foot kind of leaves the ground, your toes are kind of the last thing to make contact with the ground before you step forward. So we call that toe off. We're about to draw arms on the previous one. Okay. The next stage, once your toe kind of leaves the ground, your foot, your leg, your whole leg is swinging forward. And so we call this, well, technically we call this the swing phase. But at the peak of the swing phase, you kind of tuck your leg into your body to make it easier for your leg to kind of swing forward. So we call this knee flexion. Okay. And so there's a part of when you're walking, when your whole foot, your whole leg is kind of tucked into your body. Okay, so that's maximum flexion of the knee. Kind of a little bit exaggerated. That looks like his whole leg shrunk. Let me do that a little bit better. It's a little bit exaggerated, but that's kind of what it looks like. Okay. Right, and then as your leg kind of swings forward, and then eventually your foot's going to make contact with the ground again, and then you just kind of return to the front of the cycle. Okay, so at this point, we repeat. And so at this point, we do foot contact, which again kind of brings us back to the beginning of the cycle. Okay, so this kind of cycle, this is kind of the cycle that your leg kind of goes through as it's walking, and it just kind of repeats this, as you kind of move forward. Okay, and you can kind of see from the dotted line that your other leg is doing the exact same process. That's just kind of offset a little bit. Okay. Okay. So these are all kind of the important events of the gait cycle. We can kind of describe this a bit further. Okay? So there are two kind of stages that kind of happen. Okay. So the first stage is characterized by these three events right here. Okay. And so this is what's called the stance phase. Okay. So the stance phase takes up about 60% of the entire cycle. I'm just going to close it over. So by stance phase, what we mean is that your foot is making contact with the ground. So for every instance or every event in that phase, your foot, at least one part of it, is making contact with the ground. Okay. The 60% means that when you're walking, your leg is 60% of the time your leg is going to be making contact with the ground. Okay. The other phase. Okay. So all the way from toe off to knee flexion, to swinging forward, right up until your foot contacts the ground again. This is called the swing phase. Okay. And then just by kind of simple math, we can see that the swing phase takes up 40% of the walking gait cycle. Okay. So when you're walking, your foot spends more time in contact with the ground than it is kind of moving forward. Okay. Now, of course, just by this, just by this kind of knowledge here, by this kind of breakdown, and just knowing that your other leg is doing the exact same thing during the gait cycle, you can kind of start to see that there's a portion of the gait cycle where both of your feet are actually on the ground at the same time. Okay. And so we call this the double support phase. Okay. And so in total, it makes up about 20% of the entire gait cycle. Okay. All right. So the double support occurs, there's a portion kind of on the early basically when both feet are on the ground, we're kind of at the beginning and end of the stance phase for any particular length. Okay. All right. So that's kind of a big characteristic quality of the walking gaits, that you do have this double support. It's a lot more stable because you have 2 feet on the ground, but it's going to limit your speed. Okay. Later on, when we get to running, so we'll probably cover running on Wednesday. Running is kind of the opposite, and so in running, there's actually a portion of the running gait cycle where neither of your legs are on the ground. And so we call that flight, because there's a portion where none of your body's contacting with the ground. You're literally kind of flying forward. Eventually your leg has to come touch the ground for balance and all that stuff and gravity, but that's kind of the difference between walking and running. Where walking, you have double support, and running, you have flight. Okay. All right. Any questions on this? Okay. All right. So let's do a few more definitions. Okay. So anytime you have a given motion like this, there's often a lot of terminology that kind of comes with it. Okay. So the terms that we're going to talk about, over the next, 5 minutes are specific to just walking. And so, a lot of these terms aren't going to apply to, swinging your shoulders or throwing a punch or anything like that. Right. But, there's just a lot of terms that kind of go with it. Okay. Especially for such kind of a very common motion like walking. Okay, so let's go over some of the terms. Okay, so some of these are terms that we've already kind of seen. It's just now we're putting words to the definition. Okay, so the stance phase for any particular leg during the walking gait is when that leg is making contact with the ground. And I don't know why I put fence there. What a weird word. Phase. Okay. Okay. Number 2 is the swing phase. Okay. So swing phase is the opposite. That's the portion of the gait cycle where the foot is off the ground or does not make contact. Okay. All right. So those are the main phases. So stance phase, swing phase, and double support. Okay. So double support is not kind of different from the stance phase. It's just a portion of the stance phase where where both feet are in contact with the ground. Okay. So there's only 2 phases. There's only stance and swing. Stance and swing phase are only kind of describing just one particular foot. But then there's kind of the double support where both the stance phases for both the feet kind of align together and they're kind of happening at the same time. Okay. Okay, so let's talk some kinematic terms. Okay, so let's talk about the step length. So step length is the direction along the line of progression, between 2 consecutive footprints. So basically how much you travel in one step. All right, so you take one step, you measure how much you travel in that's your step length. Okay. All right, next one is the stride length. So stride length is the distance traveled in one gait cycle. So that's basically one step from each leg. Okay. So typically, if you have longer legs, your step length and your stride length is going to be longer. Okay. All right. Next is the step frequency or the cadence. Okay. So this is basically, how quickly you're taking steps, and so this is the rate at which foot contact events occur. So the way that we kind of measure how quickly you're walking is, how quickly you're bringing your foot to the ground. Okay. The reason, that's kind of become standard to kind of measure the running rate or kind of the speed is because oftentimes, when you're doing, gait analysis or just biomechanic analysis in general, we make use of a device called a force plate. And so a force plate is basically just like a very dynamic scale that you put on the ground. And then when your foot goes in contact with it, the scale has to kind of exert a normal force back up to your body to kind of support your weight, right? And that's something that you can very easily kind of measure. And so the step frequency is defined based on, how quickly these events occur. And just because it's very easy to kind of pick this up from a data graph from a force plate. Okay. All right, number 6 is the stride frequency. Okay. And so stride frequency is the rate at which, the gait cycles are completed, right? Remember, stride length is the distance traveled in one gait cycle or 2 steps, 1 step per foot. The stride frequency is how quickly you can go through the gait cycle. Okay. All right, and the last one, the last term that we're going to go over for kinematics is the walking speed. Okay, so the walking speed is simply just the forward velocity. So you're walking from point A to point B. What's the kind of the average speed or the average velocity that you're taking to, complete that journey? Okay. So your velocity when you're walking, if you take the instantaneous velocity, it's going to fluctuate, right? Because depending on whether you're swinging forward, whether your foot's contacting, if you actually look at someone walking, with a very kind of close eye, it kind of almost looks kind of jerky a little bit. And so the person will kind of step forward, they'll kind of stop a little bit and then walk forward, right? Normally we don't see this just because the way that we perceive walking, we perceive it as kind of walking with a kind of a constant velocity. But the instantaneous velocity of walking can be a little bit uneven. So when we're talking about walking speed, we're talking average walking speed, right? And so the way that we compute it, there's a couple ways that you can compute it. And so you can take the step length and then multiply it by the step frequency. Okay. That makes a lot of sense because in each step, you cover a distance that's defined by the step length. And then when you multiply by the frequency or the rate at which those steps are occurring, that's going to give you the walking speed. Okay. You can also compute it from the strides. And so you can either compute it from the step or you can take the stride length and then multiply it by the stride frequency. right? So whichever you use to compute the walking speed, you want to make sure that that the terms actually match up. And so it's very common to take the step length and multiply by the stride frequency, and you're thinking, wait, like why is my walking speed so slow? Or when you take the stride length and you multiply by the step frequency, and you end up something with really high. So just be careful, when you're multiplying these things. These are very simple formulas, but sometimes, with very simple formulas, you kind of make silly mistakes. And so just make sure that you're multiplying the right numbers with each other. Okay. All right. So some typical numbers, for most people, walking speed is something that varies kind of person to person, right? It's also something that you can vary yourself dynamically, right? So you can walk slowly to a place, you can walk fast, quickly to places. But on average, there's kind of a typical walking speed for most people. Okay. Okay, so walking speeds for most people are going to vary between 1.2 to 1.4 meters per second. Okay. Of course, it depends on various factors, right? So for some people, a certain amount of frequency is comfortable for them, so they may be able to execute, steps faster. Some people just have longer legs than others, and so their step length is going to be longer. But on average, the walking speed is between 1.2 to 1.4 meters per second. Okay. Okay. All right. Any questions on the walking term stuff? Yeah.
So in general, stride length should, and stride frequency, or stride length should be like twice what the step length is.
Exactly.
Stride frequency would be like.
Yes, typically. So that's assuming that both your legs are kind of symmetric to each other, but there's situations, not necessarily that one leg is longer than the other one, but there might be injuries or something like that that's preventing someone from stepping, their right foot might move slower than their left foot. And so, or they may be only be able to step so far with one foot, but then can make a big step with the other foot as well. Okay. All right, so that's the basics of walking. So that's all the typical kind of stages that occur during the gait cycle, and these are the terms that we use to describe it. Okay. All right, let's get into a little bit more analysis stuff. So let's talk about ground reaction forces. Okay. So ground reaction forces are a very essential part to human movement, okay? In particular, walking as well, right? Because the idea with walking is that you're going to propel your center of mass, or you're going to propel your body from point A to point B, okay? By itself, that's impossible for your body to do with simply just your muscle force, right? Because if you're talking just forces that are generated within your body, your muscles are technically all internal forces, right? And so when you exert a muscle force, technically there's an equal and opposite force that occurs within your body. So it's impossible to move your center of mass strictly with just your muscles by themselves. Okay. And if you don't believe me, think, well, this is going to be possible for most people, but maybe it'll be possible in the future. But if you're in an astronaut suit and you're in space, try to move from point A to point B without hanging on to something or pushing off something. It's impossible to do with just your muscles, right? And so even though your muscles are generating the forces that you need to move forward, the actual forces that push your body forward come from the ground most of the time, right? And so the ground often provides the necessary external forces that's needed to propel your body from point A to point B. And so the way it typically works is that your muscles will exert a force, that force will be driven straight into the ground, and then the reaction forces from the ground are what move your body forward, okay? Okay. And so, of course, measuring these ground reaction forces is a very kind of essential part to analyzing human movement, okay? And so, like I mentioned before, the main device or the main, apparatus that we use to measure ground reaction forces is called a force plate. Okay. And so if you've never seen a force plate before, it's basically just kind of like a scale, right? And so, a scale is a device that you use, in your bathroom, at the gym, to measure your weight, right? And so essentially you can consider it to be, you know, like a platform that you step on, and there are, usually some springs, maybe some, piezometers or kind of electric, most force plates and most scales nowadays are digital, okay? So there may be some variable resistances here. Okay. And then when you step down, right? So let's say that you have your foot here and stepping down on the force plate. Okay. So just like a scale, right? A scale is able to measure, you know, the upward reaction force, right? So that's basically how scales work. So you step on the scale, and the scale, based on the springs or based on the circuitry on the inside, measures the amount of vertical force that's needed to support your weight. And then that's the number that kind of is kind of repeated to you or shown to you in the scale. Okay. But what force plates can actually do is that there's actually some additional springs or additional measurement devices kind of parallel to the ground as well. Okay. So not only can you measure the vertical force, it can also measure in-plane forces as well. Okay. And so what you get, or the kind of the output from a force plate, is you get the ground reaction force from the ground as a vector. And so usually that vector will have, it's obviously going to have a very large vertical component because, the ground has to support your weight, but there's also going to be a horizontal component as well. And so if you're walking forward, and so if you're doing any kind of human motion, the force plate is going to pick that up. Okay. So this F ground here has vertical and horizontal components. Okay. All right, so that's something that your scale, your typical bathroom scale typically can do. So your typical bathroom scale only has springs, and only has sensors on the bottom, and so it's only able to measure the vertical force. But force plates can actually measure front to back or horizontal forces as well. Okay. The other thing that force plates have that typical scales don't have is that they are much more finely tuned. And so, they're able to take measurements, at a much faster rate than a typical scale. Okay. So that means you can obtain kind of information on how this ground reaction force is varying, down to kind of the millisecond oftentimes. Okay, because a lot of human motion, it happens very, very quickly. So even walking, right? So if after the class is done and you kind of walk out the classroom, think about how long your foot actually makes contact with the ground. It's not a lot of time. And during that time that your foot's in contact with the ground reaction force you're going to see is going to vary very, very wildly as well. And so it's very important for these force plates to be able to take these measurements very, very quickly. Okay. Okay. And so what can you do with this information? And so with the ground reaction force information, you can use that to compute things like, accelerations or, other stuff. All right. So we'll be talking about these varieties of ways, over the next few weeks, but just to kind of give you a little bit of a preview, right? So the first thing, the first obvious thing that you can do is that you can use the ground reaction forces to compute kind of the overall kinematics of the human body. And by overall kinematics, I mean things like, the velocity, the acceleration, the position of the center of mass, okay? Right, so you can do things like mass of the entire body multiplied by the acceleration of the body is equal to the ground reaction forces. Usually, if you're just walking kind of unimpeded, the only other force that's acting on your body is gravity. So you can make kind of a very simple kind of equation of motion that way. And so, with the force plate, you're able to measure this guy. Okay. So with the force plate, you're able to measure the ground reaction forces. And so it's a very simple thing to compute, what's the acceleration of the body, as the person kind of goes through the walking motion. Okay. Okay. Another way that you can use this data is you can use it as an input for some more finer, what I call inverse dynamics calculations. Okay. So inverse dynamics is something we're going to cover in a few weeks, maybe two and a half weeks. Inverse dynamics is kind of very similar to what we did in the first half of the class, where we have this position. In this case, now we have this motion. And what we're interested in is, what are the muscle forces and what are the joint reaction forces that are needed to generate this motion. Okay. And so in order to do inverse dynamics, you need to have some kind of input. And the input that is often going to be provided by some kind of force plate or maybe some kind of other, other way to kind of measure an external force. Okay. Okay. All right. So let's look at the data. Okay. So for a typical person, so for a typical walking gait, we can compute the vertical and horizontal reaction forces, throughout a gait cycle. Okay. All right, you're going to see a lot more graphs, from here on forward, just because motion is something that changes with time. Okay, so no longer are we looking at kind of a snapshot. Now we're looking at a motion that takes place over a period of time. Okay, so on the horizontal axis here, I have time. On the vertical axis here, I have the ground reaction forces. Okay. And it doesn't quite matter what the units are, but let's just say it's newtons, just to keep it all SI. Okay. So I'm going to draw two graphs here. And so first graph I'm going to compute or draw for you is the vertical reaction forces. Okay. So let me go ahead, let me draw this first. So let me go ahead and draw a horizontal line. Okay. So that's our 0 line. So I know I drew the horizontal axis at the bottom, but we're going to have some negative forces as well. So just so the graph doesn't interfere with the labels, I drew kind of an extra line. Okay. Now for the vertical reaction forces, all of our vertical reaction forces here are going to be positive, just because when the foot is in contact with the ground, remember the ground has to support your weight. Okay. So the vertical reaction forces throughout the gait cycle look something like this. Okay. So you can see it has kind of a double, bimodal kind of shape here. So there's kind of an initial peak, and then it goes down a little bit, and then there's another peak right there. Okay. So this first peak, right? This first peak is when your heel first touches the ground. Right. So when your heel first comes into the ground, the ground kind of has to stop the momentum of your body kind of falling downwards. And so that's why there's kind of a spike there. Okay. There's kind of a little bit of a lull kind of in the middle. Okay. And then right near the end, there's kind of another spike of the ground reaction forces. This is right before toe off. Okay. Because what's happening at toe off, right before your toe leaves the ground, you are pushing off your toe. And so you're using your muscles to really kind of push and exert a lot of force into the ground. Okay. And so that's going to register a peak in the ground reaction forces as well. Okay. So that's the vertical forces, and so you can see they're always positive. Okay. There's never a point during the gait cycle where the ground is pulling you towards the ground. That would be kind of weird. I mean, gravity pulls you towards the ground, but it's not the same as the ground. Okay. Now for the horizontal force is actually quite interesting. So there's a portion of the gait cycle where the horizontal reaction force is actually negative. Okay. And then it goes positive, and then it goes down towards the end right there. Okay. So this is the horizontal forces. Okay. So why is there a negative portion, right? So the idea when you're walking is to move forward. So why is it there's a portion of the gait cycle where there's a negative force from the ground, right? Well, that negative force there, if you look and see where it's correlated with the other events kind of up above, you can see that the negative horizontal force occurs, when your heel first touches the ground. Okay? Okay. And of course, by negative horizontal force, I mean a force that kind of pushes you backwards. Okay, so why is that? So when your heel touches the ground, this is, think about kind of what's happening during the gait cycle. So right before your heel touches the ground, your foot is kind of swinging forward, right? And so as your foot swings forward and as it hits the ground, there's a portion of the gait cycle where your body kind of has to slow the momentum of your leg. Okay. So, usually when you step forward, you're not really controlling your legs all that much. And so there's a lot of kind of excess forward momentum, that you need to kind of slow down. And so that negative force there is kind of meant to slow down or kind of break your momentum, just to make sure your foot can kind of make good contact with the ground. Okay. Now this forward portion, okay, so when the horizontal reaction force is positive, this is when your foot, is actually pushing off the ground, and the ground is actually propelling your center of mass forward. Okay. Okay, so that's the typical kind of ground reaction force graph that occurs during walking. Okay. All right. Any questions on this? Yeah.
This would just be for 1 foot?
This is 1 foot. Yes. Yeah, and it's only during the stance phase. So of course, during the swing phase, your foot is off the ground, and so when your foot is off the ground, we can't really measure anything because there's no contact there. Mhm. Okay. So this is really fascinating because when it's kind of broken down like this, we basically have functions here of the vertical reaction force, so-called as vertical, as a function of time. Okay. And we have the horizontal forces as a function of time as well. Okay. We can do some really interesting information with this because, even though, oftentimes we're not going to have a mathematical expression for this, so we're not going to have an actual function of time, but, we have data points that represent the forces of the function of time. Okay. What you can do at this point is you can numerically integrate these things to compute things like velocities and positions. Okay. Because what do we know, right? We know that force is equal to mass times acceleration. Okay. And so if we've measured the force, right, what we can say is that the acceleration is equal to 1 divided by the mass multiplied by the force, right? Right? We're just taking the force, we're dividing by the mass of the body. Then what we can do, if we integrate this, right? And so if we integrate this with respect to time, right? We know the left-hand side, the integral of acceleration with respect to time, this is just the velocity. Okay. So we have velocity is equal to integral of 1 over mass times the force as a function of time, dt. Okay. And then if we integrate this one more time, right, the integral of velocity is just position. Right? Now, of course, this is velocity and position of the center of mass, but we can actually get expressions for these and kind of see how they vary as a function of time, right? Just by taking our simple kind of force, our ground reaction force data, our force plate data, and just doing some simple numerical integrations here, okay? Okay. Now what we can do is we can take this information and we can work on it further, right? Because now that we have velocity and positions, we can compute things like, let's say that we compute kinetic energy. Okay. And so I'll call this E sub K, right? So for kinetic energy. What's the formula for kinetic energy? So if we have a point mass, the formula for kinetic energy is 1/2 the mass times the velocity squared, okay? Okay. And then we have potential energy, call it EP, okay? Now, there's lots of different kinds of potential energy. Potential energy is kind of a term that's used, kind of thrown out a lot in applied science and mathematics. But I'm talking about just regular gravitational potential energy here. Okay. So gravitational potential energy is just the mass times gravity times the vertical position of the body. Okay. Right. So this is going all the way back to physics 225, your first kind of physics class in mechanics. Okay. Now we can compute these. Okay. So from our force data, remember our force data, it's not just a single measurement for force. It's how the force kind of evolves as a function of time, right? From that data, we can compute things like the velocity and position. So we can compute how the velocity of the center of mass changes with time, how the position of the center of mass changes with time. Okay. And then we can take those results and just simply multiply, we can either square it and divide by 2, multiply by the mass, we get the kinetic energy as a function of time, and we can get the potential energy as a function of time as well, okay? So now we're really starting to get into kind of overall dynamic analysis, okay? So not only just kind of observing a particular motion, we're really doing analysis in terms of the energetics and the, and the forces and the, and the kinematics of the entire thing, right? Okay. So why am I bringing this up, right? So why am I bringing up all these kind of different things that you can do with force data? Well, turns out if you compute these two energies in particular, you're going to see a very kind of interesting pattern that occurs throughout the Gait cycle. Okay? So if we take these two results and we kind of plot them on the same curve, so we're going to plot the evolution of kinetic and potential energy throughout the Gait cycle, okay? Or I guess through in the next plot's going to be throughout multiple Gait cycles. We actually get a curve that kind of looks like the fall line. Okay, so once again, I'm going to make a curve here. So on the horizontal axis, we have time. Okay. And then on the vertical axis, we have energy. Okay. The exact units of energy don't really matter all too much, but we'll stick with the SI unit. So the SI unit for energy is joules. Okay. Okay. So let me plot out kinetic energy first. Okay. And so, like I mentioned, depending on if your foot is in contact with the ground or whether it's swinging, your kinetic energy actually goes up and down, for a particular foot throughout the Gait cycle. Okay. All right. So it looks something like this. Okay. So you can see the kinetic energy for a particular foot will go up and down throughout the Gait cycle. Okay. So usually, when the kinetic energy is at the peak, this is when your foot is swinging forward. So the peak of kinetic energy occurs when your foot is off the ground, when you're kind of swinging it forward. That's when it has the highest amount of velocity. Okay. Okay. And then the opposite, of course, is true. And so when you're at the kind of the valley of kinetic energy, that's when your foot is on the ground. So that's when not usually a lot of motion is occurring. Your foot is in contact with the ground. You're driving forces into the ground, so the kinetic energy is not that high usually at that phase. Okay. Okay. Now let's draw potential energy. So potential energy, it's not exactly as closely lined up as this is what I'm going to draw, but it's pretty close. Okay. So in blue here, this is the potential energy. Okay. I guess I forgot to label the orange curve. So the orange curve here, this is kinetic energy. Okay. You can see that the potential energy actually follows kind of almost like an opposite curve. So when the kinetic energy is peaking, the potential energy is in a valley. And when the kinetic energy is in the valley, the potential energy is peaking. Okay. And so you can kind of infer from this that, the portion of the Gait cycle where the potential energy is the highest is the stance phase. Okay. So that's when your foot is kind of firmly planted on the ground. You're kind of pushing off that foot. And so by pushing off that foot, you kind of raise the center of gravity for the for just the leg itself. Okay. And you kind of, enter a peak of potential energy there. Okay. All right. So this is kind of the typical graphs that you're going to get if you measure kinetic and potential energy of kind of a typical person that's walking. Okay. Okay. So of course, the main thing that we can obtain for this is that the kinetic and potential energy for a particular foot is out of phase with each other. Okay. That means when one is peaking, the other is in a valley. When the other is in a valley, the other is peaking. Okay. Okay. But that kind of brings a very important kind of observation, because even though they're just because they're out of phase, right? If you take their sum, right? So you add the total amount of energy, that's occurring during walking, right? But if you have two graphs that are kind of almost completely offset from each other, and they're kind of, peaking and valley, peaking, they're at their max and min at opposite times. If you add them up, what you're going to see is that the amount of energy that's in walking is almost constant. Okay. So that's a very, very interesting observation. And so, if you were to just look at the pure, just kind of kinematics, if you want to just look at the pure kind of, forces that are required, this means that there's no need to inject new energy into the system once you've kind of started to get walking. So, once you kind of get a walking motion going, in theory, you shouldn't have to exert any additional energy to do that. Okay. Okay. So that means in theory, once you kind of start walking, in theory, you should be able to walk forever, and you don't need to have any additional energy. Now, of course, we obviously know that's not true, right? So this kind of very simplified model here doesn't take into account things like muscle fatigue. It doesn't take into account things like friction, right? So remember, we talked before, we can kind of already see in this graph here that, just by walking, there's a portion where your body kind of needs to stop itself to kind of, prevent your whole body from kind of toppling whole. So there's a lot of additional energy expenses that's required, that's not taken accounted for in this kind of graph here. But, walking just by itself is a very, I would say energy efficient way to kind of move your body from point A to point B, right? Normally, when you see people going around, you see them walking around campus, most of the time you don't see people running or jogging from point A to point B, right? Now, that's not always true. Sometimes people are in a rush, they need to get somewhere, they need to run. But for the most part, most people are walking just because it's the most energy efficient way to kind of move your body from point A to point B, okay? And this graph here kind of confirms that fact. And so one way that you can kind of interpret this graph is that when you're walking, you're kind of making there's kind of a constant exchange, right, between kinetic energy and potential energy. Okay. So there's kind of a trade-off. So there's certain parts where you trade some potential energy for some kinetic energy, and then there's parts where you're going to trade some kinetic energy for potential energy. Okay, but there's this constant kind of payoff between the two. Okay. So what does this remind us of? Right? There's actually a very simple device that kind of mimics this behavior almost perfectly. Right? It's a device that you've seen, many times, I think, in your previous classes, and that is a pendulum. Okay. And so if you look at a pendulum, right? So by pendulum, I just mean kind of a very simple, just a weight that's on a string. Okay. And then what you can do is you can kind of pull the pendulum up, and it's going to rotate kind of, between these kind of two extremes right here. Right. And so if it's a simple kind of gravity pendulum, you pull it upwards, it's going to fall down and then come back up, and then fall down and come back up. Right. Eventually, it's going to stop because of air resistance and friction and things like that. But odd times you can keep it going for a long time. Okay. Now, if you look at this pendulum here, right? If we look at these particular phases right here, so let's look at these phases first. Okay. So in those phases, basically there's going to be a brief moment in time in those phases where the pendulum is motionless, right? So there's going to be zero velocity, and that occurs when the pendulum reaches maximum height. So here we can say that the pendulum is in a state of maximum potential energy. Okay. But then as the pendulum moves, right, it's going to reach the zenith, or it's going to reach the bottom of the pendulum itself. Okay. And so when the pendulum is in this state, the potential energy is at a minimum because that's the lowest point that the pendulum can go, right? Because it's constrained by the string. But it's at this point where the velocity of the pendulum is maximum because it's trying to get to the other side, right? And so during this part right here, the kinetic energy is maximum. Okay. Right? Because that's where the velocity is maximum. And so if you look at this, this looks very similar to what we understand about walking, right? And so when we come back on Wednesday, what we're going to see is that you can take this kind of very simple concept of a pendulum, and you can actually start to make some really interesting models for walking. And so we're going to go over what's called the ballistic walking. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all I got for today. So thank you guys for coming. Wednesday, I'll bring back your midterms, so make sure you come back for those. So thank you guys for coming today. And hope you guys have a good rest of your day.
What do you need to get from today, sports?
Well, yeah, I got it, but at the same time, it's a lot easier. It's more cost efficient for easier.
Wednesday, but I was going to go over here today.
I'm not going to finish today. I'm probably not going to finish. I'll probably Wednesday. I'll bring it back again next week. So I'll bring it for the next week.
Yeah, I saw it 20 million times before.
So I checked one problem for correctness on homeworks every week. And so it's just kind of a random problem.
Yeah.
So I checked the same one for everyone. So I don't think you guys need to do problem for your.
Because I submitted 2 files.
Oh, okay. Everything in.
And that's what I have like auto.
Oh, okay. Oh, sorry. Yeah, I must have missed that.
Do you want me to just submit it in one file or?
That would be a bit more convenient, but that was my fault. I just missed that.
Okay.
Can you send me an email and then I'll go and revise your.
Oh, thank you.
Different words, same thing.
As promised.
Oh, yeah.
Yep.
This is nice. This is a nice material.
Yeah.
It's the wrong way though.
Just came in today.
Nice. This is really nice. Thanks, guys.
Of course.
Yeah.
So the plane's supposed to be going downwards though, it's the way.
No, but you wanted to go up. Right? This
Yeah,
was
no,
fun.
it felt.
It's gonna happen. You gotta update. Nice guys, it's really nice.
Or let me know if that one doesn't fit. I have all the other different sizes.
Okay, no, it looks, no,
Okay, cool.
yeah, nice guys.
Thank you.